Hello students, this is lecture 4 in basic chemistry series for NSEJS and NTSE or any Olympiads you are preparing for. So understanding of electronic configuration is very important. So in this lecture we'll be dealing with electronic configuration. Before that, we will try to understand the quantum numbers. What are quantum numbers? So quantum numbers are basically like the pin code of any person. If you mention the pin code, that's the address of a person, right? So it's like the address of a person. For example, if there is a person over here, right, and if he is living in certain locality, how are you going to find him, right? First you need to find out in which city he lives, then in that city in which locality, and that locality will also be divided into many wards. So in which ward, and in a particular ward, the ward will be divided into many buildings. In which building, then if you are able to reach that building, then in the building there are many floors. On which floor, so you need to go to that particular floor also. Then on that floor there are many rooms. Which room, then you'll be able to reach this person. Basically, if you want to find a person residing in a city or in a village, suppose this person resides in Bangalore, right? So how are you going to find him? For that you need address. First you need to, out of many cities in India, you need to go to the particular city which is Bangalore. Now in Bangalore there are many localities, there are many areas, like Shishadripuram is there, Indranagar is there, Jayanagar is there. So out of many localities, suppose this person lives in Jayanagar, so you will go to Jayanagar directly, right? After that, the Jayanagar is also further divided into many wards. Ward number 1, ward number 2, ward number 3, ward number 4, like that. So assume that this person lives in ward number 7. So out of many wards, you'll go to the ward number 7, right? You go to the ward number 7 and you find there are many buildings, right? Building number 1, house number 1, house number 2, house number 3. So assume he lives in house number 5. So you'll go to house number 5. Suppose that house number 5, that building has many floors. So out of many floors, he lives on second floor. If let's assume that, so you'll go to the second floor, and on second floor you'll find many rooms. So suppose that he is living in room number 202. Then you will be able to reach that person. Same way, quantum numbers gives us the complete address of an electron in an atom, right? Where what is the complete address of an electron will be told by the quantum numbers. Quantum numbers helps us to reach a particular electron of a particular atom. So there are 4 quantum numbers. We are going to deal with each one of them one by one. So first one being the principal quantum number. We'll see one by one. First one being principal quantum number. It will be denoted by N. Second one is azimuthal quantum number. It is also known as subsidiary quantum number. It will be denoted by L. The third one is magnetic quantum number. Q number is quantum number denoted by M. And the fourth one, the last quantum number, is spin quantum number denoted by MS or simply S. So these are the 4 quantum numbers which will be giving us the complete address of an electron in an atom. Let's see what are they. So the first quantum number is the principal quantum number. Principal quantum number is denoted by N. For your understanding at NSEJS or any junior Olympiads level, understand that the principal quantum number will tell us, this tells the shell number. what is the main shell number, that will be told by the principal quantum number, right? So for example, this is nucleus. We already know the nucleus will be represented by a circle and a plus sign in it, plus positively charged there. Around it we know that there are many shells, right? Okay, so the very first shell from the nucleus, this one will be said to be first shell, or n equals to 1, or the value of principal quantum number is 1. The second one will be said to be second shell, n equals to 2, third shell, n equals to 3, like that, right? So if n tells us the shell number, n is a positive integer. It must be an integer because it's a counting number, right? So it's a positive integer. The value of n will never be negative, right? It will always be positive integer. So the value of n can go from 1 to infinity. The value of, because a particular atom can have infinite number of shells. So first shell, second shell, third shell, fourth shell. If I have to say what is the value of principal quantum number for the seventh shell, it's simply n equals to 7. Fine. So principal quantum number will tell us the shell number. Next. Second one is azimuthal quantum number. Denoted by L. Now what does azimuthal quantum number tells? Azimuthal quantum number will tell us the division of a shell. Means a shell is further divided in the same way, like suppose that this is a particular area. This is a particular area. Suppose this particular area is known as JEE-Nagar. It's a JEE-Nagar area. Fine. Now the JEE-Nagar area will have many colonies over there. So the blue things that you see over here, they are roads. They are road number 1, road number 2, road number 3, right? There are many roads over there, correct? Now there are some other streets also. These white lines are streets crossing these roads, right? So JEE-Nagar, assume that JEE-Nagar is an atom. Assume JEE-Nagar is an atom. Now we need to find a person, and these green things are buildings. They are buildings on different roads. Fine. First thing is that suppose JEE-Nagar is an atom. What we are assuming that JEE-Nagar is an atom, right? Now in this atom there are many roads over here we see. So let's assume they are road number 1, road number 2, road number 3, and so on, correct? Now I need to find a person who is living in this particular building here in red, right? So first thing, if I need to find this person, do I need to go to the road number 2? Yes, I need to go to road number 2. So I will go to the second shell to find this person, right? So we'll go to n equals to 2 now to find this person. But on road 2, we have the information that the person is living on the second road, but in which building? There are many buildings, you see. Building number 1, 2, 3, 4, 5, 6, 7, 8. There are many buildings. Out of many buildings, the person is living in the 6th building, right? Can we say that a shell over here, or the road, is further divided into many buildings, right? A colony is divided into many buildings, right? So same way, a shell is divided, and the division of shell is called subshells. The division of shells is called subshells. So I will say that the person over here lives in 6th subshell of second shell. If we need to find this person, we'll go to the second shell and then to the sixth subshell. The second shell is divided into many subshells. Now, so this is what the subshells means. This is what the azimuthal quantum number deals with, right? It deals with the division of a shell. It deals with how many subshells are going to be there in a particular shell. A given shell will different shells will have different numbers of subshells. What will be the number of subshells in a given shell will be indicated by this quantum number, azimuthal quantum number. So let's see. So L, which is azimuthal quantum number, it deals with the division of shell, and division of shell is called subshells. That means we'll simply say that many subshells make a shell. Many subshells will come together to make a shell. Fine. Remember that the value of L, which is the azimuthal quantum number, it depends on shell number or simply principal quantum number, because shell number is denoted by principal quantum number. So the value of L is going to depend on the shell number. How does it depend on N? So remember this, the value of L goes from 0 to n minus 1. The value of L will go from 0 to n minus 1. All the integers between 0, including 0 also, all the integers from 0 till n minus 1 will be the values of L. We'll try to understand it through an example. So, for example, suppose we are talking about the second shell, n equals to 2. So, value of L should be from 0 to n minus 1, right? Or 0 to, what is the value of n over here? It's 2. So 0 to 2 minus 1. So 0 to 1. All the integers from 0 to 1 are just they, 0 and 1, right? So value of L is 0 and 1, right? So how many values of L we have? So we can say that there are 2 values of L, right? Fine. If I find about the third shell, the value of L should go from 0 to 3 minus 1, n minus 1, right? So 3 minus 1, because the value of n is 3 over here, or 0 to 2, right? All the integers from 0 to 2, so is it 0, 1 and 2? So these are the values of L for third shell. So in third shell, the value of L will be 0, 1 and 2. There are 3 values of L, right? If you have to take n equals to 4, the value of L will be 0, 1, 2 and 3. 0 to n minus 1. There are 4 values of L. Now what does this mean? The number of values of L. So remember this, number of subshell in a given shell is equal to the number of values of L. It will depend on the number of values of L. How many values of L? Remember, how many values? I'm not saying what values, right? I'm saying how many values of L you have for a given shell. Same number of subshell will be there in a given shell. For example, in fourth shell, the value of L will be 0, 1, 2 and 3, 0 to n minus 1, right? How many values of L we have? Do we have 4 values of L? So we will say that fourth shell has 4 subshells. Fourth shell will have 4 subshells. Fine. Another example, for third shell, For third shell, the value of L will be 0, 1 and 2. Right? We have 3 values of L. So, can we say that third shell has 3 subshells? In a similar way, you just find the number of values of L. The number of values of L will tell you how many subshells are there in a given shell. Fine. So we understood that how do we find the number of shells or subshells in a given shell, right? Now, one more thing we need to remember that there are, if we talk about the subshells, there are majorly 4 subshells. Right? There are majorly 4 subshells. There can be more also, but whatever elements we have till now, all of those elements, their needs can be sufficed by just these 4 subshells. In later classes, you will understand that how. Right? What are those subshells? Those subshells are S subshell. S stands for sharp. There are P subshells. It stands for principal. There are D subshells. It stands for diffused. And there are F subshells. This stands for fundamental. For now, you can just keep this in mind. You can just use it for a knowledge what are the full forms of the SPDF, right? We will not be using it quite frequently. Just remember there are 4 subshells, S, P, D and F. SPDF are 4 subshells. There can be, remember, there can be more than these 4 subshells, but these 4 subshells suffices the needs of all the elements which are discovered till now, right? Now, so since they are subshells, they must be having some relation with the azimuthal quantum number. Why? Because azimuthal quantum number deals with the subshells only, right? So remember, if the value of L is 0, it's S subshell. S subshell will always have the value of L equals to 0. L equals to 1 is P subshell. L equals to 2 is D subshell. L equals to 3 is F subshell. Remember these values of L. We will be using it soon. So, S subshell, the value of L will always be 0. Value of L will be 1 for P subshells. Always be 2 if it's D subshells. 3 if it's F subshell. Right? So, for example, if somebody asks you, if they ask, what are the subshells in the first shell? So, if you want to find the subshells, you will always find the values of L, right? Because L only deals with the subshells. So, L will be 0 to 1 minus 1, n minus 1, right? The value of n is 1, or simply 0. We have just one value of L. So, first thing is very clear to us is that the first shell has just one subshell. Question is, which subshell is there? Since the value of L is 0, I'm not talking about the number of values. What values of L is there? There is just one value of L, 0. For L equals to 0, is it S subshell? So, first shell has just one subshell, which is S subshell. Now, how will you denote first shell having S subshell? 1S, this 1S denotes this number here, denotes the shell number, and this denotes the subshell. So 1S is the subshell, S subshell belongs to the first shell, right? If I talk about the second shell, L will be 0 and 1, 0 to n minus 1. So the value of L is 0 and the value of L is 1 also. How many values we have? We have 2 values of L. That is why the second shell will have 2 subshells. Right? Now, what are those subshells? L equals to 0 is S subshell. So, do we have 2S? 2S means it's a subshell. Remember, 2S is a subshell. S subshell belongs to the second shell. And 2p, p subshell from the second shell because L equals to 1 is there, right? Similar way, n equals to 3, L will be 0, 1 and 2. So can I say that in third shell I have 3 subshells, and what are those subshells? Are they 3s, 3p and 3d, right? L equals to 2 is d, but this d belongs to which shell? Third shell, that's why 3d. L equals to 1 is p, but the p subshell belongs to which shell? Third shell, that's why 3p, right? L equals to 0 as it belongs to third shell, that is why 3s. Likewise. Fine. So this was about the azimuthal quantum number. We'll keep that in mind. The third quantum number is magnetic quantum number. Now, magnetic quantum number will be denoted by M. Now, what does it denote? What is the use of magnetic quantum number? So, magnetic quantum number, it indicates the division of a subshell. Like the azimuthal quantum number used to denote or indicate the division of a shell, and the division used to be called as subshells. Now the magnetic quantum number will deal with further division of subshells, right? This will deal with the division of subshell. Now just remember that example where the JEE-Nagar was there, right? JEE-Nagar, we assumed JEE-Nagar as the atom. There were many colonies over there, right? So we went to road number 2 to find that person, right? In the road number 2, we went to the 6th subshell or the 6th building to find the person. Now, is the building, this is the 6th building, just assume, and it is divided into many floors. Suppose there are 3 floors over there. Just assume there are 3 floors over there. So out of 3 floors, he should be living at one of the particular floor only, right? Now, which floor is, can we say that this particular subshell is divided into, there is further division there into floors over there? There will be many buildings on any shell. There will be many buildings, right? Every building will have either 1 floor or 2 floor or 3 floor or 5 floor, right? So every subshell is divided, every building over here is divided into floors. So in the similar way, every subshell is divided into orbitals. The division of subshells are called orbitals. So suppose if the person lives on the 2nd floor, we'll say that the value of M over here is 2. He lives on the 2nd floor, right? Now, orbitals, there are many orbitals will come together to make a subshell, and many subshell will come together to make a shell, right? Now, division of subshell is called orbitals. We'll keep that in mind. And remember, this is different from the orbits. Orbit is nothing but shell only, right? And it is one of the major unit, right? It's one of the main thing. Many orbitals are the fundamental things over there. Like many floors makes a building, similar way many orbitals will make a subshell, and many subshells will make a orbit or a shell, right? So orbitals are the smallest unit over there. There is no further division after the orbitals. Remember that, right? Now, so we'll be focusing on orbitals, and magnetic quantum numbers will help us to find the number of orbitals there, right? So the magnetic quantum number, since it deals with the division of a subshell, so it must be depending on the number of subshells, right? Or the value of azimuthal quantum number. So the value of M will depend like this. It will go from minus L to plus L, right? Write all the integers from minus L to plus L, correct? For example, L equals to 0. It's a S subshell, we know that. Now we need to find out how many orbitals are there in the S subshell. So for that, we'll write M should be from minus 0 to plus 0. It's the same thing. You have just one value of M, correct? In a similar way, if you have to find out for the P subshell, the value of M will go from minus 1 to plus 1. Now write all the integers from -1 to +1 including 0. So can we write it as -1, 0 and +1? We have three values of m over here. Similar way, you can find for the L equals to 2 also, which is D subshell. So for L equals to 2, will you have -2, -1, 0, 1 and 2, 5 values of m, right? Similar way you can find for the L equals to 3 or F subshell also. Fine. Now what does the number of values, like the number of values of L, used to denote the number of subshells in a shell? In a similar way, number of values of m is equal to the number of orbitals in given subshell. How many orbitals a given subshell will have will be told by the number of values of m. For example, S subshell. How many values of m we have over here? We have just one value. Number of value is just 1, right? So if the number of values is just 1 over here, so S subshell will have just one orbital and we will call it S orbital, right? S subshell has just one orbital. Why? Because it had just one value of m. We see here it had just one value. For P subshell, the number of values of m you can check is 3. There are 3 values of m. So P subshell will have 3 p orbitals. There are 3 p orbitals in each P subshell. Remember that. In D, if you check, there are 5 values of m. So we'll say that there are 5 d orbitals in each subshell, in each d subshell. Similarly, if you find for the F subshell, for which the value of L is 3, the value of m will be -3, -2, -1, 0, 1, 2 and 3. We see that there are 7 values of m, so there are 7 orbitals in each d subshell, right? So from these, do we gather an information which is that here we have the subshell, a table we have subshell and number of orbitals. So S subshell had just one orbital, we have seen that. Fine. P subshell has 3 orbitals, we have seen that. D has 5 orbitals and F has 7 orbitals, right? Each S subshell will have one S orbital, each P subshell will have 3 p orbitals, each D subshell will have 5 d orbitals, each F subshell will have 7 f orbitals. Keep that in mind, right? Remember the 3s, 1s, 2s or any s, let's take 7s. These all are subshells. They are not orbitals. Keep that in mind. Which subshell are there? They are S subshells, right? Okay. So if S subshell has just one orbital, so you will not get confused by these numbers over here, 3, 1, 2, 7. You will not get confused by them. They are just the shell number. They are just the shell number. That is 3s belongs to the third shell, 1s subshell belongs to the first shell, 2s belongs to second shell, 7s belongs to seventh shell, likewise, right? So everywhere, since one S subshell has a capacity, one S subshell has one S orbital, so 3s also had just one orbital only, because it's ultimately a S subshell, one S subshell, right? It's a one S subshell. Although it belongs to the third shell, but still it's just one S subshell. Similar way, 1s had just one S subshell, 2s also had just one S subshell, 7s had also just one S subshell. Keep this in mind, because people usually get confused when they are writing, when they are using it in the electronic configuration. So similarly, if I say the 2p, 3p, 6p or any p, right, it just denotes one p subshell. These numbers over here denotes the shell number. 2p belongs to second shell, 3p belongs to third shell, 6p belongs to sixth shell, but the number of p subshell in each of these is just one, and one p subshell contains 3p orbitals. Let's keep that in mind, right? Similarly, it will go for the D and F also. So you don't have to get confused by these numbers. These are the values of principal quantum numbers. 2, 3, 6. These all are the values of principal quantum number. They are just telling you that this S subshell belongs to the first shell or second shell or fifth shell, like that. Fine. So this was about the magnetic quantum number. Now we are going to learn about the last magnetic quantum number, which is spin quantum number. Spin quantum number, let's denote it using S. Right. So remember that electrons are revolving around the nucleus like the planets does, we know that, and electrons are also revolving around its own axis. What does this mean? Let's see this. So over here we have a nucleus. Let's take one shell over here. Suppose this is the electron over here, right? This is of course revolving around the nucleus, which is the first statement, right? One more thing is there. It has one axis. The axis will be there, which will be passed through its central portion, the imaginary axis, of course, right? It is of course revolving around this, around the nucleus, but also it is moving, it is rotating along its own axis also, right? It is rotating along its own axis also, and also it is revolving around the nucleus. Fine. So that is the second statement. Now, what does the statement means? The spin quantum number deals with this, the spin of electron, right? It's revolving around its own axis. As the name suggests, it deals with the spin of an electron along its own axis. So this deals with the spin of an electron along its imaginary axis, right? Now, if an electron is rotating along or spinning, there can be just two directions possible, right? Either there can be clockwise spin, either the electron is spinning in the clockwise direction. We will use this sign to denote the clockwise spin of the electron by convention, okay? This upward arrow will denote the clockwise spin of the electron, or the another possible direction is the anti-clockwise spin. We will use this arrow, the downward arrow, to denote the anti-clockwise spin of the electrons. Fine. One thing you should keep in mind for now, you will learn it later in the physics also, that spinning charges, if the charges moves or they are spinning, they will generate magnetic field around it. They generate magnetic field around it. Fine. If they are generating a magnetic field around it, remember that magnetic field, like the magnetic pole you have heard, like you have heard about the magnetic pole, right? So same pole of the magnets repel. In the similar way, magnetic field in same directions, if you have two magnetic fields coming from two sources, and if they are in the same direction, they repel, they will repel with each other. But the magnetic field in opposite directions will attract. Remember, magnetic field in the same direction will repel, magnetic field in the opposite directions will attract. So we know that electron, if it is spinning, it will generate some magnetic field. So let's assume that this electron is generating the magnetic field in this direction, in outward direction. Of course, it will be generating its magnetic field in all the directions, right? So the green color arrow is the electron and the yellow color arrow are the directions. Basically, it is generating the magnetic field in all the directions. You see that it's going in outward direction. Fine. If I take another electron with the same spin, will it have the same direction? Yes or no? Same electrons spinning in the same direction will generate the magnetic field in the same directions, outward directions only, right? But if I take electron in the opposite directions, the direction of the magnetic field will become just opposite, inward, right? So, can we say that electrons with same spin will repel? Why will they repel? Because we see that the electrons with the same spin will have the direction of magnetic field in the same directions, and the magnetic field in the same directions will repel each other. Then you see that the electrons with the opposite direction spin, they have the magnetic field in the opposite direction. So the magnetic fields in the opposite directions attracts. So can we say these two electrons will attract each other, right? So we'll say that electrons with opposite spin will attract. Let's keep these two statements in mind, right? You also understood the logic. Why? Fine. So electrons with the opposite spins will attract. Fine. Okay. Now let's see how do we representation of an orbital. How do we represent an orbital? So we use the square diagram to denote an orbital. Correct. We'll use square, just a square, to denote an orbital. For example, if I say S subshell, S subshell had just one orbital, right? So this is S subshell, S orbital. One square block is one S orbital, right? It can be 3s, it can be 4s, it can be 1s, anything. All the S subshell had just one orbital, we know that. If I had to denote P subshell and its orbitals, right? So we know that a P subshell has 3 orbitals. So a rectangle over here, we divide it into 3 squares. So it's suppose it's 3p. So these 3 are the orbitals of P. Similarly, you can denote the D subshell using 5 blocks. 5 blocks, right? Suppose it's 3D or 4D or 5D, anything, any orbital. These blocks are what? Orbitals. Similarly, you can show the F subshell also. F subshell will be, we know that there are 7 orbitals, right? It can be either 4f, 5f, anything, right? Any f orbital. So these blocks are the number of orbitals there. We can see that P subshell has 1, 2, 3 orbitals. D has 1, 2, 3, 4, 5 orbitals. F has 7 orbitals, like that. S has 1 orbital. Fine. Now, let's see what is the role of the spin quantum number over here. Let's assume that we are putting the first electron in the remember, electrons are ultimately in the orbitals only, because the ultimate place in an atom is the orbital, right, where electrons are going to live. Now, so if I put electron with the clockwise spin, just assume, can it accommodate the another electron with the same spin? No, it cannot. The 3s cannot accommodate the electron with the same spin. Why? Because they are going to repel. They are in the same direction, right? So is it understood that we need another electron with the opposite spin? Then only they will attract? Yes. So the another electron will go with the opposite spin. Fine. Now let's check if I am able to put the third electron or not in the 3s. So if I take the third electron, so it will have either the clockwise spin. If I take clockwise spin, it will be repelled by this electron. There will be repulsion. So this electron will not be allowed in this. Okay, what is the another possibility? I can take the electron with the opposite spin now. If I take this electron in the orbital 3s, this will be repelled by this electron. So what do you see that the third electron is not allowed in an orbital, right? This is going to happen, this same thing is going to happen with all the orbitals over here, right? Because if any orbital contains an electron, suppose the clockwise spin electrons, right, another electron you must bring with the opposite spin, then only they will attract. If you are trying to bring the third electron will have either the clockwise spin, it will be repelled by the another electron already in the orbital which has the clockwise spin, or if you try to bring the electron with the anti-clockwise spin, which is the third electron, if you're trying to bring that in, that will be repelled by the electron which we already have in the orbital and it has the anti-clockwise spin. So what can we conclude? Can we conclude that any orbital can accommodate maximum of 2 electrons? So we'll say that any orbital, may it be S, P, D, F, any orbital, S, P, D, F, any orbital can accommodate maximum of 2 electrons. This is very important. There are questions asked on this many times, right? So any orbital, may it be S, P, D or F, it cannot accommodate more than 2 electrons. Let's keep that in mind, right? Any orbital will always, whether it's S orbital, P orbital, D orbital or F orbital, it will always contain the maximum number of, that is the maximum capacity of any orbital, right? So it's 2 electron. Now since different subshells has different number of orbitals, so will that decide the maximum capacity of subshells now? So let's see over here. Let's have a table. Now, here we have the subshells. Here we have the number of orbitals. And here we have the maximum capacity. We are talking about the maximum capacity of a subshell now, right? We already know the maximum capacity of any orbital is 2, right? It's 2. So as subshell had just one orbital, we know that. So maximum capacity, should it be one orbital maximum containing 2 electrons, so 2, right? P subshell, we know that it has 3 orbitals. So maximum capacity of P subshell, should it be 3 into 2 equals to 6 electrons, right? D has 5 orbitals, so it will be having the maximum of 10 electrons, each orbital containing 2 electrons, right? F has 7 orbitals, so the maximum capacity of 7 orbitals will be 14 electrons, right? So these are the maximum capacities of subshells. Remember, subshells. S subshell will have a maximum capacity of 2 electrons. P will have a maximum capacity of 6 electrons. D will have a maximum capacity of 10. F will have a maximum capacity of 14, right? There was a question asked in some examination, some competitive exam. The question was, what is the maximum capacity of 3D orbital, right? Options were 2, B were 30, C were 10 and D were 5. Any options, right? Now what do you see? The question is quite tricky. See, just if you read the statement saying the 3D orbitals, right? Whether it be any orbital, it will have a maximum capacity of just 2 electrons, right? Maximum capacity of a 3D orbital will be 2 electrons, right? Don't confuse it with the subshell. It's not 3D subshell. If it were 3D subshells, then the answers would have been 10. but since it's about the orbitals, that's why maximum capacity is 2. So that was about the quantum numbers. We'll be using these quantum numbers in the next lecture when we are dealing with the electronic configuration. There we will be learning how do we write the electronic configuration. Do remember, electronic configuration is very, very important to understand the properties of any element, where to identify whether something is a metal or non-metal or a metalloid, what kind of ions they are going to form. We have already seen in the previous lecture about the concept of ions, right? In the next class, next lecture, we'll be seeing how do those ions, why do those ions form a particular type of ions only. Sodium, why do sodium always forms Na plus only, aluminium always forms Al plus 3 only.